AI Paper Podcasts. Today's paper is Code2Math. Can your code agent effectively evolve math problems through exploration?
Large language models are currently hitting International Mathematical Olympiad, or IMO, levels of reasoning.
But the industry has hit a massive wall. We're running out of challenging, high-quality math problems for training and evaluation.
Manual creation by human experts is simply too slow. The solution presented in this paper is a multi-agent framework.
We give code agents, specifically models like DeepSeek Reasoner and Gemini 3 Pro Preview Thinking, access to Python environments to autonomously evolve existing math problems into significantly harder ones.
The result is that these agents successfully synthesize new, mathematically sound problems that surpass their own solving baselines.
This forces solver models to use massive amounts of compute and tokens to find the aha moment, proving that code-driven exploration is a viable, scalable engine for synthesizing high-difficulty reasoning data.
If you are training reasoning models, you need the synthetic data. It is a critical breakthrough for the test time scaling paradigm.
All right, let's take a breath and transition into the architecture behind this. Because for the AI researchers and ML engineers listening, this multi-agent framework is basically the blueprint for breaking through our current data bottleneck.
It really is. And I think the first thing to clarify is that this isn't just standard text prompting.
Right. You can't just ask an LLM to make a harder math problem.
Exactly. When you do that, the model typically just swaps a variable, like changing a 5 to a 50,000.
Which adds tedious calculation but zero conceptual depth.
Exactly. So to fix this, the researchers utilized the small agents framework to build a 3-agent system.
And they gave this system a Python sandbox. That is the crucial part.
It's everything. They equipped it with heavy-hitting mathematical libraries, SIMPy for symbolic mathematics, Z3 for theorem proving, NetworkX for graph logic, and iter tools.
So the agents are actively writing code to test their mathematical hypotheses in real time.
Right. And the division of labor across these 3 distinct agents is what makes the whole system function. The first component is the evolution agent.
Which needs a starting point, right? A seed problem.
Yeah, a seed problem. The researchers collected about 100 of these from rigorous sources, standard advanced textbooks, regional competitions, the AM and the IMO.
So already starting with hard data.
Very hard data. The evolution agent takes a seed problem and analyzes the solution to find what they call the cognitive bottleneck.
The cognitive bottleneck. So it's essentially looking for the conceptual leap required to solve it.
Yes. And it does this by applying theory of mind.
Oh, that's fascinating.
It is. The agent is explicitly instructed to anticipate the exact reasoning path an experienced human or an AI solver would naturally take.
So it figures out what you're going to try to do.
Right. And once it understands your expected path, it deliberately conceals the insight. It creates a new burden of discovery.
A burden of discovery. I love that term.
It engineers an aha moment that is intentionally elusive. It shifts the problem from just applying standard formulas into something that requires a structural leap.
But, and I'm sure every engineer listening is thinking this, engineering a complex trap is completely counterproductive if the resulting problem is mathematically broken.
Oh, absolutely. A broken math problem is worse than useless for training.
Which brings us to the second agent, the solvability verification agent. And honestly, looking at the paper, this seems like the most critical engineering component of the whole framework.
I would argue it is. It operates in 2 strict phases to ensure the evolution agent hasn't just hallucinated a paradox.
What's phase 1?
Phase 1 is static problem analysis. The agent checks for surface-level domain errors. It looks for undefined operations.
Like denominators equating to 0.
Exactly, or geometric constraints that inherently contradict each other in physical space.
Basically a simple sanity check on the boundaries.
Yeah, a fast filter. Which is necessary before you spend compute on phase 2, which is the deep logical audit.
The deep logical audit. How does that work in the Python sandbox?
In this second phase, the solvability verifier independently evaluates the proposed solution's steps. It uses Python and SIMPy to execute and verify algebraic transformations step by step.
So it's actually doing the math.
It is proving the math. A flawless logical chain here proves the problem actually can be solved.
And if it finds an error?
If the verifier detects what the paper calls a transformation error or a case of boundary neglect, the evolved problem is instantly rejected. The rollout just terminates.
Boom, done. But preventing mathematical errors only solves half the problem, right?
Yeah.
Mathematically sound generation isn't automatically useful for training reasoning capabilities.
No, it could just be incredibly boring math. That necessitates the third piece of the framework, the difficulty verification agent.
Right, because we want to avoid that lazy generation problem we talked about earlier.
Exactly. This agent utilizes a strict 5-point scoring mechanism. Scores 1 and 2 are flat out rejected because they represent artificial complexity.
Artificial complexity. That's exactly what we see when a model just makes the numbers larger or adds tedious algebraic layers.
Or requires a solver to repeat a simple loop 10 times instead of once.
Right. From a machine learning perspective, it's like adding more layers to a neural network without actually improving the architecture. It takes longer to compute, but it isn't conceptually deeper.
That's a great analogy. Penalizing that artificial complexity ensures the agent doesn't mistake labor-intensive algebra for an intellectual challenge.
So what does it take to get a passing score? A 3, 4, or 5?
To pass the verifier, the problem must demonstrate genuine cognitive depth, and what the researchers term anti-templating.
Anti-templating, meaning it must force the solver to abandon rote templates and recognize heuristics.
Yes, achieving a perfect score of 5 demands an elegant mathematical leap, like connecting two previously disparate mathematical fields to find the solution.
Okay, so just to recap the system for you guys listening, we have an evolution agent generating the problems, a solvability agent verifying mathematical integrity, and a difficulty agent filtering out tedious algebra in favor of true cognitive depth.
That's the Smologen's triad, yeah.
And then the researchers used an external state-of-the-art model, specifically GPT 5.2 High, to blindly judge the final outputs.
Right, to verify the internal system's effectiveness.
Let's talk about the results, because the data here is wild.
The agreement rate, or AR, is what we look at first. It measures how often the internal verification agents matched the judgment of that external GPT 5.2 High model.
How did DeepSeek Reasoner do as the evolution agent?
When DeepSeek operated as the evolution agent, it achieved an agreement rate of 94 out of 98 on solvability.
That's roughly 96%.
Yeah. And when Gemini 3 Pro preview thinking was used, it hit a perfect 98 out of 98 agreement rate.
100% agreement rate from the Gemini model. That indicates the internal verification agents are highly, highly reliable.
Extremely robust. They serve as an exceptionally strong filter against invalid generations. It means researchers can actually trust the mathematical soundness of the synthetic data being produced.
And the reliability of that data pipeline leads to what I think is the most mind-bending finding in the paper for ML engineers: capability asymmetry.
Capability asymmetry is a massive concept.
Let's break it down. It essentially means that these code agents can autonomously construct mathematical challenges that exceed their own solving baselines.
Yes. By utilizing code-driven exploration and iterative hypothesis testing in their Python sandbox, they engineer a burden of discovery that they themselves might struggle to overcome later.
Or entirely fail to overcome.
Right. When they are evaluated strictly as a solver model, without access to that evolutionary scratchpad, they fail on the very problems they created.
The implication there is profound. A model can build a puzzle that is structurally sound, yet too complex for its own deductive reasoning to unravel without the step-by-step scaffolding it used to create it.
And we saw this in the testing data. When the researchers tested the models on the newly evolved problems, accuracy dropped significantly across the board.
I have the numbers right here. When Gemini 3 Flash Thinking was tested on problems evolved by DeepSeek Reasoner, its accuracy plummeted by 21%.
A massive drop. Even the highly capable GPT 5.2 High experienced an accuracy drop of 6 to 9%, depending on which underlying model generated the evolved problems.
I was looking at the average token consumption metric alongside that accuracy drop.
Yeah.
You can clearly see a fat tail distribution forming in the high token region when models attempt to solve the evolved problem.
Compared to the original seeds, yes.
Right. And for the ML engineers listening, think of this like the shift from training compute to inference compute in reasoning models. The evolved problems force the solver out of efficient low-token template retrieval.
They cannot just pattern match their way to the answer anymore.
Exactly. They are forced into prolonged test time computation.
The solver models have to engage in extensive hypothesis testing, symbolic manipulation, and self-correction just to uncover that necessary aha moment.
The cognitive engagement deepens significantly. It proves that the anti-templating strategy enforced by the difficulty verifier was highly successful.
It was. And to really make this concept of anti-templating concrete, I think we need to walk through a few specific case studies from the paper.
Let's do it. The structural leaps these agents made demonstrate exactly what a burden of discovery looks like in practice. Let's start with case 1.
Case 1 is great. The original seed problem was a standard competition algebra question. It was about finding integer points on a simple quadratic curve, basically a parabola.
And it asked the solver to prove a specific inequality regarding points located on the left side of the axis of symmetry.
Right. It is a highly recognizable template for anyone who has trained on competitive mathematics. The solver immediately knows to apply basic properties of parabolas.
It's rote memorization at that level.
Exactly. However, when Gemini 3 Pro Preview Thinking evolved this problem, it elevated it from a quadratic to a cubic structure.
Okay, so bumping up the polynomial degree.
But more than that. The new problem asks the solver to find the minimum possible area of a triangle formed by 3 distinct points on the graph of a cubic function, specifically y equals x cubed plus nx squared.
And it constrains the x-coordinates to be integers strictly less than the inflection point of the graph.
Yes.
The structural leap there is brilliant. For an ML perspective, imagine mapping a simple, lower-dimensional classification problem into a much higher-dimensional latent space where the decision boundaries entirely change.
That's a perfect way to visualize it. The agent took the straightforward concept of the axis of symmetry from the quadratic and translated it to the inflection point of the cubic curve.
But the real trap is the area of the triangle constraint.
Right. The aha moment requires the solver to realize that the area of that triangle on the cubic curve factorizes in a way that perfectly mirrors a collinearity condition.
So to solve it, you have to synthesize geometry, modular arithmetic, and product minimization all at once.
Standard quadratic templates are completely useless here. You have to actually think.
Case 15 is even crazier. It offers an even clearer example of the agent engineering a psychological trap for the solver.
Oh, the game theory one.
Yeah. This evolution was based on a seed problem from the IMO 2025. It featured a scenario called the inequality game between two players, Alice and Bazaz.
Right. In the original problem, the constraints change based on parity, whether the turn number is odd or even.
On odd turns, Alice chooses a number bounded by a linear constraint. On even turns, Bazaz chooses a number bounded by a quadratic constraint.
Because it is a classic parity-based game, the strategy is relatively trivial to deduce.
Yeah, the player restricted by the quadratic constraint only ever has one move before the constraint resets back to the linear player. The decision tree is incredibly shallow.
Very shallow. But the code agent analyzed that shallow decision tree and fundamentally altered the environment. It changed the rule from odd and even turns to whether the turn is divisible by 3.
Modulo 3.
Under the new rules, Alice plays on turns 1 and 2, and Bazaz plays on turn 3.
By shifting to modulo 3, the agent introduces a massive strategic degree of freedom. The player with the quadratic constraints suddenly has 2 sequential moves instead of 1. This forces the solver to choose between 2 distinct strategies. A concentration strategy, where they play 1 massive move and 1 zero move, or a distribution strategy, where they play 2 equal moves.
And in machine learning terms, it's the classic exploitation versus exploration trade-off. But the loss landscape has been secretly inverted.
That inversion relies on the arithmetic mean quadratic mean inequality, the AMQM.
Yes. For those less familiar with the specific theorem, the AMQM inequality states that the arithmetic mean of a set of non-negative real numbers is always less than or equal to their quadratic mean.
Because of the way the agent structured the quadratic bounds across 2 turns, standard intuition from the original parity game strongly suggests using the concentration strategy.
It bait and switches you. But the AMQM inequality dictates that the distribution strategy is actually mathematically optimal for maximizing the bound across the 2 turns.
So the standard intuition leads the solver straight to the wrong answer.
The agent utilized theory of mind to anticipate the heuristic the solver would apply, and then restructured the mathematical environment to ensure that specific heuristic would fail.
It's almost devious.
It really is. Let us examine one final example, case 16, which demonstrates adding dynamic layers to static problems.
This one originated from a problem in the Chinese Mathematical Olympiad, the CMO.
Yes. The seed problem involved red and blue cards with initial values. In each operation, you select a red card and a blue card, and you replace both of their values with their average.
And the objective is to find the minimum starting number of cards required to make the sum of the red cards exceed 100 through these averaging operations.
It's a static combinatorial bound problem. You establish the invariant, calculate the maximum possible gain per operation, and work backward.
Pretty standard. But the evolution agent transformed this by introducing a third element, green cards.
Green cards, complete with their own initial values and interaction rules with the red and blue cards.
At first glance, Adding a third color just sounds like the artificial complexity we discussed earlier, just making it tedious.
Right, but the inclusion of the green cards elevates the problem from a static combinatorial identity into a dynamic asymptotic stability analysis.
Because the operations must now occur in distinct phases. The non-trivial trap the agent engineered here is a quenching effect.
The quenching effect. It means that the value gained from the first phase of averaging is decayed or actively reduced by the necessary interactions in the second phase involving the green cards.
For the ML engineers listening, you can visualize this exactly like a degrading learning rate or the vanishing gradient problem in a deep neural network.
Oh, that's a brilliant way to frame it.
You might make massive updates to your weights in the early layers, which is the first phase of averaging. But as that signal propagates through the deeper layers involving the green cards, the gradient decays towards zero.
You cannot just apply the original static formula twice. The solver has to understand linearity and error propagation over time.
The structural depth required to map that decay is a massive leap from the original CMO problem.
It perfectly demonstrates shifting the burden of discovery away from algebraic manipulation and toward a fundamental understanding of dynamic interacting systems.
It's incredible. Having agents that can write code, test hypotheses, and output IMO-level mathematical problems with this level of structural depth is a massive leap forward.
It is.
However, we do need to ground this discussion in the computational overhead required. Code-driven exploration at test time is highly computationally intensive.
Very much so. The efficiency metrics detailed in the paper reveal the true cost of this evolution. Generating these high-quality problems is not a one-shot process.
Not at all.
On average, the system experiences between 1.56 to 6.55 failures to get exactly one successful, fully verified, evolved problem.
The agents are given a strict budget of 20 attempts per seed problem, right?
Yes. While some of the simpler evolutions powered by DeepSeek Reasoner only took 1 to 3 failures, the highly complex cases like engineering that AMQM trap or the asymptotic stability analysis often required over 10 iterative rollouts before a valid problem was produced.
And the solvability verification agent is responsible for the vast majority of these rejections.
Exactly. Formulating a conceptually deep idea is relatively easy for an advanced LLM. But translating that idea into a mathematically flawless execution is incredibly brittle.
The slightest error in boundary conditions, a missed edge case in the Python code, or a subtle logical fallacy in the proposed solution path causes the solvability verifier to terminate the rollout immediately.
And highlights a strict trade-off between exploration efficiency and difficulty enhancement.
If you instruct the agent to push the boundaries of its latent space to engineer a deeply complex aha moment, its hypothesis testing in the Python sandbox will inevitably lead to mathematical dead ends.
The rigorous dual verification system guarantees the final output is pristine, high-quality data. But the high failure rate defines the current frontier of what agentic workflows can handle efficiently.
So to summarize the core value for the researchers and engineers building the next generation of reasoning models, code-driven exploration is now a proven, scalable engine.
It is. It permits LLMs to utilize Python as a computational whiteboard to systematically discover hard-to-find mathematical insights.
This framework successfully synthesizes a new curriculum of data that directly addresses the IMO-level data bottleneck the industry is currently facing.
And I think the success of this framework leads to a highly provocative concept regarding the future of AI training data.
Yeah, let's talk about that. We have firmly established this concept of capability asymmetry. The observable fact that LLMs possess the ability to consistently engineer structurally sound mathematical spaces that completely surpass their own deductive limits.
Right. So if models can iteratively engineer environments they cannot solve, could self-evolving code agents eventually drift into synthesizing entirely new mathematically valid subfields that human mathematicians haven't even conceptualized yet?
Just generating completely novel spaces.
Exactly. They could theoretically generate axioms and test implications in spaces far beyond human intuition.
But the limiting factor, of course, remains verification.
Yes. Will the immense computational overhead required to strictly verify the logic in these ultra-complex, entirely novel spaces ultimately halt the self-play loop?
Because the agents can propose the unknown. But computationally proving that the unknown is structurally sound remains the ultimate bottleneck.
It does.
Solving that verification bottleneck in novel mathematical spaces is undoubtedly the next great challenge for the field. Thank you for joining us for this deep dive into the paper on AI Paper Podcast. We will catch you next time as we continue tracking the bleeding edge of machine learning research.